Okay, here we go. So last time the Canvas quiz concerned this graph here. This is the caterpillar's path on the wall. And so the y-axis is like height, and the x-axis is like distance to the right, or horizontal distance. So the question is this a function? Is this a function? Does this graph show the graph of a function? So yes. How yes? Or no? How no? No, Nick knows. Is it a function or not? Dylan?
It's not a traditional function, but it is a parametric function.
Okay, so it depends, right? It depends on the question. If you're asking, is y a function of x? Is y a function of x? Yes or no? No, right? Because for given values of x, there's lots of cases where you get more than one value of y, right? It's unpredictable, right? So given an x, there's multiple values of y. But we learned last time about these things called parametric functions, right? So how could it be a function? How could it be if it was thought of parametrically? T could be like time since the caterpillar started moving. And then what's the dependent thing? So independent, time, dependent. What could it be? Could the dependent be thing? So this is a function. At any given time, the caterpillar only has one location, right? Location on the wall. But that location needs two variables, right? It needs a horizontal and a vertical component. So if you think of this graph as t is the independent variable and ordered pairs x and y are the dependent variable, then it's a function because given any time, the caterpillar can't be in two places at once, right? Given a time, there's only one location on the wall that the caterpillar could be. Does this make sense? Okay, so this opens up like a whole new realm of possible graphs that we could have, right? That before we said weren't functions. So really any path crazy like this can be thought of as a function if your independent variable is this like parameter and the dependent variable then is location, or in this case ordered pairs x and y. So let's just look at some more of those here. So here's another example. Okay, now so this is not that crazy. If you look at it parametrically, it's not that crazy, right? X is just t plus sine 2t, and y is t plus sine 3t. Okay, but when your x and y coordinates are determined in that way, you get this graph, right? So is it a function or not? Is it a function? Yes or no? Is it a function? Yeah.
It's not a function in the Cartesian sense, but in a parametric sense it is.
Right, so I showed you right here. So given any value of t, do you see that there's only one x and y that you get for any value of t? Yep. But, of course, there's lots of values of x here where you get multiple values of y. What about, is x a function of y? Given a value of y, is there only one x? No, that's kind of like even worse, right? It's like you got all these cases where given a value of y, you have multiple x's. So the only way you can see this as a function is parametrically. And there it is. This one. So there's one also involving sine and cosine that's periodic. So as t keeps increasing, you just keep going around this loop. There's that. Here's another function, cosine t and sine of t plus sine 5t. All right, so the days of the vertical line test are not over, but you have to consider now any graph in the xy plane could be truly a function if you think of it as a parametric function. Okay, what about this one? Is it a function? Purple. So there's the equation for this as a parametric function. Is it a parametric function? Yeah, given any value of t, you're only going to get one x and one y. That generates these points. What about, is y a function of x?
Yeah.
As far as we can see, yeah, y is a function of x. What about, is x a function of y? Given values of y, is there one corresponding x that you have? Nope, right? Because any value of y, there's two possible, not every, but there's all these values of y here have two x's corresponding to them. So y is a function of x, yes, but x is not a function of y. And there's the parametric version of this function. Okay, so notice that, so y is a function of x. Can we find it as a function of x? So what is y as a function of x? Well, y is 2 minus t squared. How could I rewrite that in terms, is it possible to rewrite that in terms of x? Is it possible? What could I do to get y as a function of x? Yeah, Freddie.
We would get in the value of t and then plug it in for x?
Yeah, so you can take this, right? So from that first equation, t equals x minus 1 all over 3. See that? And so that's what t is. I can take that and I can substitute it in there. And that gives me that y equals 2 minus what, x minus 1 all over 3 squared. And so the picture sure looks like y is a function of x, but does the actual math, the equation, confirm it? So do we truly have a function of x here? Meaning, for every x that I put in, do I only get one y that corresponds to it? Yep, right? So no matter what x I put in here, it's always going to give me just one y. Okay, what kind of function is this? Powers of x, polynomial, right? Polynomial. Do polynomials have cosine in them? Exponential functions involved in polynomials? Log functions? Nope. Remember, polynomials are sums of essentially powers of x. You can have coefficients on them. Sums of powers of x are polynomials. This is a quadratic polynomial, right? It's parabola. Now, I can, given any function of x, so say I was starting with this function, okay? Say starting with this function, an easy way to parameterize any y as a function of x is to start by saying, let's let x equal, let's let x, that's GC's way of doing it, so I don't know why I don't need to do those brackets. Let x be t. And if x was t, then what would y be? If x is t, then y is? Just replace the x with a t. And here I have another way to write this parabola, this function, as parametrically. Okay, so so both of these are equivalent to that polynomial y equals 2 minus x minus 1 squared, x minus 1 over 3 squared. So question, is this function, this parametric function, the same as this parametric function? Are they the same? are they the same or not? Same function or different functions? So if I put t equals 1 into this function, what do I get? What ordered pair do I get for t equals 1? 4, 1, right? What if I put t equals 1 into this function? What ordered pair do I get? 1, 2, right? So are they the same function or not? Different functions, right? If I put t equals 1 into a function, or any t value n, if I'm comparing that, I need to get the same result every time, right? So here I get 4, 1, here I get 1, 2. So they're different functions, but same set of points. They're just generating the same set of points differently, right? So for different values of t, I get different points, but I get the same whole set of points in the end, right? If I put all possible values of t into this one, and then put all possible values of t into this one, it'll generate the same set of points, but it'll do it differently. Okay? So, different function, but same range, same set of points that you get. Okay, so let's look at this then. So here's another parametric function. I want you to write that parametric function as an equation of x and y, and possibly y as a function of x if it works, right? So can we write y as a function of x? And then write a second parametric version of so once you get this function, write a second parametric version of that function.
Well, so for y, so that's right.
So tell me what you did. So how'd you start?
Well, solve for x.
Okay.
And then I plug that in.
So what did you get?
For x is the y.
So what'd you get then that first step? No, that first step. So you solved for t.
Yes.
T equals
X plus 3
x plus 3 all over 8. And then? Right. And so then we get? Negative 6.
Well, yeah, negative 6 and then x plus 3 over 8 minus 2.
Okay, and if we do all the math, we get?
3x minus 9 over 4.
And then I think we get, if you do all the math, I think you get 17/4 in the end when you do all the math. Someone get minus 17/4? Yep, so you're going to have, what, 24/8? No, 18/8 minus 2. Minus 18/8 minus 2, and that turns out to be minus 17/4. Okay, so is y a function of x? Yes. Y is a function of x. What kind of function is it? Linear function, right? So let's graph that line. Here we go. So that's our line. Negative 3/4 x minus 17/4. And then, do we rewrite it in a different way parametrically? Chance, you're up. Okay, so there was a, given y as a function of x, there was a quick way that we could make that into a parametric function. Do you remember what that was? Just let x be. We could just let x be t, And then if x is t, then y is negative 3/4 t minus 17/4. Okay, so same function or different function? Different functions, but
Same results.
same result. Okay, same result. So what I want you to do is, so let's prove that. So I'm going to turn the graphs on now. So our given function, I'll make blue. There it is. You see it coincides with the line there, and then second one red coincides with the line. So both of them are generating the same set of points, but differently. If we are to pick t values and plug them into both, we would get different ordered pairs each time. But if you take all t values, you eventually get all the same points. Okay, so another thing we could do to show that is we could find x prime. What's the derivative of x prime in this first case? The derivative of x with respect to t in the first case and in the second case. What about in this first case? Derivative is 8. Y minus 6. This one, x prime is, y prime is. Okay, so what negative 3/4 is? This is the rate of change of what with respect to what? He wants y with respect to t. Agree with that? And the value is negative 3/4. So negative 3/4 is the rate of change of y with respect to t. What does that mean? What does that mean? Something we worked hard on earlier in the course. Do you remember? Yes, it is the rate of change of y with respect to t. Negative 3/4. What's our meaning for rate of change? So if there were 3 things I would want you to get out of this course, this would be one of them. That whenever in the future, whenever you're thinking or working with a rate of change, that you would come up with this relevant meaning that we've been working on earlier in the course. So can you remember it? So think about it and then share with the person next to you. Everyone's talking to somebody. What's the meaning of negative 3/4 as the rate of change y with respect to t? Yes?
I don't know.
You don't know? Okay. Today's the day. Today's the day. Let's see. How about Sophia's here? Isn't Sophia sit over here? She's gone today? Is Sophia here? Okay. How about Hannah? No. You already no.
I'm not exactly sure, but is it something about accumulation?
Something about accumulation? Okay. Yeah, it has to do with accumulation. Where's Alexander Roth?
That's me. I'm not super sure.
Okay. Today's the day. All right. How about Freddie?
Is it as t increases,
Okay.
the rate of change changes at a rate of negative 3/4?
Okay, so that's not, it is the rate of change, so it's not telling us how the rate of change is changing, because it is the rate of change. So it tells us how what is changing.
As the net accumulation changes, I don't know.
Okay. How about Drew? What does the rate of change, negative 3/4 mean? Y with respect to t?
It means like however much t changes,
Okay,
you can multiply that amount of change by negative 3/4 to see how much y changes.
that's right. It's telling us how much y changes for a change in t.
I was right.
Given any change in t. Today's the day. Everyone gets it. Today, given any change in t, we know the change in y, right? Y changes by how much? negative 3/4 times as much as that change in t. And so there's an equation that embodies that meaning, which is dy equals negative 3/4 times dt. In this case, dt, right? So so when t changes, how does y change? Does it change? So this negative 3/4 tells us how y changes with respect to t. So if t increases, what will y do? It will decrease, right? And how much will it decrease compared to t? More or less? A little bit less, right? 3/4 as much, right? It'll decrease 3/4 as much as t increased. Okay, compared to, how about this one? X prime is 8. So that means what? Dx equals 8 times dt. So over here, when t increases, how does x change? Does it change a little, a lot? Does it increase? Does it decrease? So it increases a lot, right, compared to t. So if t increases, dx goes up 8 times as much as t. Here, if t increases, dy goes down a little bit less than t went up. Okay, so that's the idea of rate of change, right? It's this number that like embodies how two quantities are changing together, right? Is that dependent quantity changing? Is it increasing with your independent? Is it decreasing? Is it increasing really fast? Is it increasing slow? Etc. Okay, so this then, look at the rates of change, right? The rates of change for the original version, 8 and minus 6. The rates of change for our new version of the parametric function, 1 and negative 3/4. So again, underscoring that they're two different functions, right? Two different functions because the rate of change. So how does that play out with the function itself? How does it play out? So what's happening for the same change in t? What happens? How does this graph get produced for the same change in t versus how this graph gets produced for the same change in t? The numbers should be in perfect agreement with what you're seeing visually, right? So for a change in t, how do the two graphs get generated in comparison? Can anyone vocalize that? Yeah, Neil.
Well, the blue graph has bigger numbers, so this goes faster.
What's that? Yeah, so the right. So because for the same change in t, what x changes 8 times as much, but here x only changes like the same as the change in t, and y changes by minus 6 versus less than how much t changes. So for the same change in t, you get kind of like a lot more points from the blue version than you do from the red version. So that's why as you let t vary, then the blue points seem to be getting generated faster than the red points. Okay, but put in all real numbers for t in both functions, and what will happen? You'll get the whole line, right? You put all real numbers in the blue version and all real numbers in for the red version, and you'll get all the points. It's just that for a change in t, you get bigger intervals of the line with the blue version than you do with the red version. Okay, and that's everything to do with the rate of change, right? For a change in t, how much does x change? How much does y change? Okay, another thing to point out here is that for increasing t, this line has direction, right? So as t increases, the points are generated for this line down and to the right. And so that's an important quality of parametric functions, is that they have a direction associated with them, how they're generated as t increases. And we don't really talk about that with the y as a function of x, right? It would just be left to right always, right? So as x increases, it would just be left to right. Okay, any questions on the line? Let's pause that. All right, so what is x squared plus y squared equals 1?
Circle radius of 1.
Okay. Circle. Any particular circle? You know what that's called? Unit circle. And in pre-calc, you wrote, so is y a function of x? X a function of y? Nope. Okay. So in pre-calc, you wrote ordered pairs on the circle. You had a way of writing what x and y were for any point on the circle. Do you remember what that was? Remember what x and y, how you could write ordered pairs on the circle? Nick remembers? Yeah. So when they were teaching you that, little did you know that that was a parametric function, right? What's our parameter? What's the parameter? Theta. So theta is a parameter because it generates what? For any given theta, you get an x and y ordered pair. So this circle is a function, right? This circle is a function if thought of parametrically, where theta is the parameter. Okay, and so then we could talk about what the starting points, like for theta equals 0, the graph is started to be generated where theta equals 0 is kind of like the starting point. Where is that? 1, 0, right? Cosine of 0 is 1, sine of 0 is 0, so 1, 0. And then what's the direction of this curve? Right? This x squared plus y squared equals 1, no direction. It's just the set of points that is the circle. But x equals cosine theta and y equals sine theta as a parametric function has direction. So which way from 1, 0, which way does it go? Counterclockwise, remember? Counterclockwise. And that's by definition of theta and cosine and sine being x and y coordinate. It generates counterclockwise starting from 1, 0. So let's look at a different one. Different one. This one. So here I've got x equals minus sine pi over 2t, and cosine is pi over 2t. So how could so now I want to sketch. I want to use this parametric function, and I want to sketch it. So one thing we can do is we can look at the individual functions of x and y as functions of t. And so what value of t will give me one full period for sine and cosine? So we'll make it all the way around. What value of t is going to get me all the way around? 4, right? Because we need 2 pi, right? So t equals 4 is going to get me 2 pi. And that's convenient because we know the cycle is really broken up into kind of 4 pieces, right? The cosine and sine cycle. So 1, 2, 3, 4. And so by sketching these two and then using what's called, we can use a covariational approach, we can come up with what the parametric function would be. So now negative sine, does that, we know there's a max, midline, and min. Does negative sine start at the max, midline, or min? Midline, right? Starts at 0, the midline. And then will it go up to the max or down to the min from there? If it's negative sine. Down to the min, right? And then back to the mid, up to the max, midline. 1, 2, 3, and 4. Right? Cosine starts at the max, and there's only one place to go from there. Midline, min, midline, max. So now we're going to think about what happens as t varies. As t varies from, say, 0 to 1, and then 1 to 2, and then 2 to 3, and then 3 to 4, what are each of x and y, how do they vary? And then we want to think about plotting ordered pairs. So as t varies from 0 to 1, what does x do and what does y do? So as t varies from 0 to 1, so we're going to think about c varying from 0 to 1, from 1 to 2, from 2 to 3, and from 3 to 4. So what does x do as t varies from 0 to 1?
Goes from 0 to 1, or 0 to 1.
0 to negative 1, right? So you see this graph tells us that as t goes from 0 to 1, x goes from 0 to negative 1. And then as t goes from 1 to 2, x goes from? So what's a little bit strange here is we're putting x on the vertical axis, right? X is a function of t. So you're looking at the vertical change to look at x values, right? So x goes from negative 1 to 0, then from 0 up to positive 1, as t goes from 2 to 3, and then back down to 0. And then y? What does y do? 1 to 0, to negative 1, back to 0. This is what the graph is telling us, right? So now we have the information as t changes. We're not going to graph t, we're going to graph x and y and think about how they're changing together. So as t goes from 0 to 1, we start at, what point do we start at? 0, 1, and then x is going to go to negative 1 while y goes to 0. Do you see what that will look like? Draw it with your finger. X will go to negative 1, y will go to 0. So we're going to end up there. And it's dealing with sine and cosine, so it's still going to be circular, right? And then x will go from negative 1 to 0, and y will go to 0 to negative 1. So we'll end up here, and they'll change together like this. That was better. Okay, and then now I'm at 0, negative 1, and my x is going to go back to 1, y to 0, so I'm going to end up there. And they're going to vary together like that. And then finally I'm at 1, 0, and my x is going to go back to 0 while my y goes up to 1. So what do I get? The unit circle again, right? It's still the unit circle. What are the differences between this unit circle and the one we did before, cosine t, sine t? Different starting point is one difference. So now I'm starting here. Still going counterclockwise, so that's the same. And what else is different? There's one more big difference between this one and this one. What value, what range of t do I need to get all the way around here? T needs to go to from 0 to 2 pi. What range of t do I need to get all the way around here? 0 to 4. So it's a rate of change issue again, right? The rate of change of x and y with respect to t here is greater. So we're going to make it around the circle for a lower range of t than we did for the standard one. Okay, so what's the key to relating this to x squared plus y squared? Equals 1. Both of these parametric functions really are equivalent to x squared plus y squared, and what's the mathematical link? What's our link between cosine and sine and x squared plus y squared equals 1? Remember? So when you're making the transfer between parametric and equations of circles and ellipses, it always goes back to this. Cosine squared plus sine squared equals 1. It's the Pythagorean identity. So look, in this one, for this one we just did, if I have x squared plus y squared equals 1, what's x squared? X squared is minus sine pi over 2t squared. And y squared is cosine of pi over 2t squared. Does that equal 1? So minus sine of pi over 2t is the same as positive sine pi over 2t. So this has the form sine squared plus cosine squared. So it equals 1, and that's what the equation says, x squared plus y squared equals 1. Okay, this is terrible practice. Don't do this, but I was just trying to give you what's wrong with that. There's no arguments on sine and cosine. You would never write sine and cosine without arguments, but I'm just getting the idea, right? Okay, so if you start with a parametric and you want to write the equation in x and y, or if you start with an equation in x and y and you want to write it parametrically, it all goes back to this using this Pythagorean identity. So let's show an example of that. Where's my example? X minus 2 squared over 4. X minus 1. So what kind of graph is this? Do you remember from your pre-calculus pass? Is an ellipse. The center of the ellipse is 1, negative 2. And then it's has a longer radius in x than y, or in this case longer in y than x. So the x radius is 2 and the y radius is 3. Okay, and so I want to write this parametrically, right? This is just an equation of x and y. I want to write it parametrically, so I'm going to solve for y in terms of x, right? Is that the way to write an ellipse parametrically? Is that the natural way? No, so ellipses and circles, the natural way to write them parametrically is using sine and cosine, right? Sine and cosine. If I solve for y, I'm going to have to take a square root. I'm going to get a plus or minus. All right, and so then it's not going to lend itself to writing it parametrically, okay? Because I have to split it up. I don't want to split it up. So here's what I'm going to do. I want it to look like our Pythagorean identity, which is this, right? And then once I get it looking like that, then I can put what's inside the parentheses. I can match it up to sine, cosine, or negative sine and negative cosine, or any combination. So what do I got? X minus 1 over 2, and y plus 2 over 3. And so now it looks like the Pythagorean identity, and what I can do is I can make this plus or minus cosine t or plus or minus sine t. Either of those will work. And then depending what I choose here, if I choose a sine, plus or minus sine, then over here I'll choose plus or minus cosine, and vice versa. So again, plus or minus cosine t, plus or minus sine t, makes 8 possibilities. There's 8 ways that I could assign plus or minus cosine and plus or minus sine to these two things. And that will determine what? Starting point and direction. So I'm going to do minus cosine. This first one has minus cosine. And the second one has to be either plus or minus sine now. I'm going to use plus sine. And so now I can write it parametrically. I solve for x, right? So what is x? X is negative 2 cosine t minus 1. And y is 3 sine t plus 2 minus 2 minus 2. So there's my ellipse written parametrically. Is this plus 1?
Yeah, it should be plus.
Thank you. So there's my center, plus 1, negative 2. And there are my radius. The radii, look. 2 in the x direction, 3 in the y direction. So where will this start? Will it start at the top, left, right, or bottom? If I plug in, what? T equals 0. So if I plugged in t equals 0, I could figure out where it starts, and then if we could figure out where it goes from there. We're a little short on time, so I'm just going to show it to you here. So is that what we came up with right there? So when t equals 0 gives me the left side of the ellipse, and then this particular choice for cosine and sine means it'll generate it clockwise for increasing t. It's a little fast for my eyes there. Let's do that instead. So one way you could figure out that it's going clockwise is to take derivatives. What is dx dt? 2 sine t, right? And what's dy dt? 3 cosine t. Then we could look at what pi over 2 is going to be this top point up here, because it's, so pi over 2 gives, so at pi over 2, we'd have positive 2, and we'd have, at pi over 2, we'd have, that'd be 0. So dx dt then, positive 2, tells us, you see how it tells us that it's going clockwise? Because at the top, if t changes, then what? X changes, increases or decreases? It increases twice as fast, twice as much as t. So that would indicate it's going to the right, and that would give us the fact that it's going clockwise. One way to show that it's going clockwise.